power, power is a rate. So whenever we talk about the rate of something, we're talking about how quickly we get it done, right? So power is the rate at which work is done. Okay, how quickly we have the ability to do work. Okay, so whenever we talk about rate, we're talking about how quickly we have the ability to accomplish something. The unit for power is watt. So where do we see that most often?
Light bulb.
Right, in light or electricity, right? So the unit for power is a watt, which is a capital W. Okay, so it's kind of easy for us to get that confused with work, right? But this is a unit, so it should go at the end of our answer. Okay, a unit is 1 joule per second. So if we're looking at the equation for power, which I'll give you here in just a second, you'll see that we'll take 1 joule divided by 1 second to give us a watt. We also can measure power in horsepower, and so where do we see that most often? Cars or engines, right? So engines have a certain horsepower rating, right? That means that's the maximum rate at which they can convert that energy. Okay? So the conversion between horsepower and watts, you'll need to have that down. Okay, 1 horsepower is equal to 746 watts. Okay, so when you convert from watts to horsepower, you should divide by 746. If you need to go from horsepower to watts, you would multiply by 746. Right? The number of watts should always be larger than the number of horsepower. Okay, horsepower doesn't have a real specific unit except that the unit is watts, but we don't talk about it except for just with an HP. Okay, we don't have to label it with anything really besides HP. Okay, but it still is measured in horsepower. Okay, so if we would convert that to horsepower, we would just say it has a 1 HP rating, right? That's what its horsepower is. Okay, so when we find power, our equation is work over time. Okay, so the equation for power is really work over time. And there's a few different ways that we can solve for work, and that's what we're going to look at today. Remember last class we talked about work. We could solve for work using the equation force times displacement. We could solve for work using the equation change in kinetic energy. Right? There's a couple different ways that we can solve for work. So when we say that power is work over time, right, it could be any of these ways to solve for work over time. Okay, so there's lots of different ways we can go about solving for power. Okay, but it's work over time. And so when we think about work, right, work is essentially the energy that's been transformed. So we can think about it in terms of the transformation of energy over time. And that's going to make a little bit more sense when we look at potential energy today. Okay, it's important for you to understand that power and energy are not the same thing. Okay, a person's work, right, the amount of work that a person can do is limited. So when I say we're going to do work, right, that's applying a force over a distance, or that's changing our velocity or something like that. Why is a person's ability to do work limited? Yeah, that's right. You only have so much strength. You only have so much energy. Your body can only convert energy at a certain rate. Like we have little individual horsepower ratings, right? Our equation for power here. And I want to walk through this real quick before we look at this problem. Power is work over time. So that's the initial equation I gave you. Right? We said that you could solve for work by using force times displacement. So all we did here was substitute force times displacement in for that. Does that part make sense? Okay, what does this look like? Displacement over time. Velocity. It looks like velocity, right? So all we did from here to here is substitute. You can solve for power by taking the force applied times its velocity. So this equation needs to go on your equation sheet as well. Okay, that bottom one. So this can make some of your problems really simple, right? If we apply a certain force that brings it to some velocity, right, that's our power output. Okay, so this says a student used 140 newtons to push a block up a ramp at a constant velocity of 2.2. what's their power output. So that means it's really just as easy as it seems, right? We're going to take force times velocity. Okay, and what would my units be for power? Watts. Yeah, watts. Okay. 308 watts. So what would happen if I wanted to convert that to horsepower? What would I have to do? I would divide by 746. Okay, so if I wanted that in horsepower, 0.413. Okay, and this problem didn't ask me to do that. I'm just telling you if for some reason we needed to, that's how we'd go about doing that. Okay, so 308 watts. Okay, an electric motor lifts an elevator 9 meters in 15 seconds by exerting an upward force of 12,000 newtons. What power does the motor produce? We've been given our force and our distance and our time. Right? So we can solve for velocity first by doing distance over time, right? If you wrote down that middle equation, it looked like this. Force times distance over time, right? We could use that one, or we could use the combination where we found velocity first. So if we did velocity, we would take 9 meters over 15 seconds and get about 0.6 meters per second. Then we could say power is equal to force times velocity. Right, you could put that all into one equation if you wanted to. That's fine. Okay. The reason we can just do distance... I'm sorry. Thank you. Uh-huh. So I took distance over time. And the only reason I can use that distance over time equation is because it was constant velocity. It wasn't speeding up or slowing down. So it's just meters over seconds. So that's really important here. If it was speeding up or slowing down, we'd have to use a regular kinematics equation to solve for velocity. But since it wasn't speeding up or slowing down, we can just do meters over seconds. Okay? Okay. We're going to shift gears a little bit now and talk about potential energy. Does anyone have any idea what potential energy means? Yeah, good. Stored energy, right? Potential energy is stored energy. And so it depends on where the item or the object is located. Okay? So we are going to talk specifically about gravitational potential energy. And gravitational potential energy depends on the position or configuration of the body and its surroundings, or the object. What that means is that if we're talking about gravitational potential energy, it's got to have the potential to have gravity act on it, right? It's got to have the potential to fall in order to have gravitational potential energy. So it has to be off the ground, essentially. Okay, it has to have the ability to fall. And so if I hold two objects, one this high above the ground and one this high above the ground, which has more potential energy, the pen or the calculator? The pen, right? It's higher, right? It's up higher, so it's got more potential energy, right? And we're assuming like maybe they have equal mass. But for right now, we need to think in terms of the higher something is off the ground, it's got more potential energy, okay? So the reason we talk about this term potential energy is that when it's above the ground, it has the potential to fall and do work on an object that it would hit, right? So let's say a brick is held in the air and it falls and hits something on the ground, right? It's probably going to displace that item, right? It's going to apply a force and move that item further into the ground, right? Or break the item or something. It has the ability to do work on it. So when something is above the ground and has the potential to fall, we call that gravitational potential energy. Okay? And the equation for gravitational potential energy is really simple. Okay, here's the equation for gravitational potential energy. You can keep the G, but I'll usually leave it off, right? We're usually going to just think about most potential energy being gravitational. But your book puts that in there, so I put it in as well. M has to be mass, and it needs to be in kilograms. G is the acceleration due to gravity, which is regular 9.8. Okay, you don't have to include the negative here. And H, what do you think H is probably? Height, good. Height needs to be in meters. Okay, and so when we talk about potential energy, we need to talk about kind of looking at where our ground level is, or where the lowest place that object could fall, and then we look at the height above or below that kind of ground level. Okay. So mass in kilograms, gravity's regular 9.8, you don't have to put the negative, and then our height will be in meters. That's really important. Okay. This little g just tells us that we're looking at gravitational potential energy. You can leave it off because most of the time we're going to use that equation for potential energy. We're only going to get one more and it looks completely different, so you'll know the difference between the two. Okay, so the H tells us that the higher off the ground an object is, the more potential energy it has, right? It does have a little bit to do with its mass, but you know, as a definite rule, right, the higher off the ground it is, the more potential energy it has. We also have the ability to connect work done by gravity as an extension of potential energy. So we talked last class about work being the change in kinetic energy. Work can also be equal to the change in potential energy. So work in and of itself is the ability to change energy, right? The ability to transform energy. So this equation should probably go on your equation sheet, one of these two, right? Change in potential energy means final potential energy minus initial. So all I did here was expand it out a little bit to look at mass times gravity and our height differences. Okay, so one of those two needs to go on your equation sheet, and this one does as well for sure. Okay. And as we talk about the transformation of potential and kinetic energy, they use an example of roller coasters a lot. So we're going to see a lot of roller coasters in this example, in this chapter. But as we look at this roller coaster, we're going to look at the transformation of energy from potential to kinetic, or using both of them. Okay, so as this roller coaster sits at the top of its path, right, if it's not in motion, it has to have all potential energy, right? Does that make sense? Not in motion means its velocity is 0, so our kinetic energy has to be 0, and it has the potential to move downward, right? So it's got all potential energy. As it reaches the bottom of the track, right, we kind of consider this our ground level because hopefully the roller coaster is not leaving the track, right? We're going to assume that we're on a somewhat safe roller coaster. And that's the furthest down that it could go, which means it has no more potential to fall, right? Does that part make sense? Yes or no? Okay. As we deal with these roller coasters, right, we're going to assume that the dip in the roller coasters is usually the ground level, right? So here you can kind of reset your ground level wherever you need to. Most of the time, it's going to be at the bottom of that dip. Then as we reach a halfway point, about here, right, we see that it has both potential and kinetic, because it still has the potential to fall downward, and it's in motion. So we're going to look at this kind of sliding scale of potential to kinetic energy. Sometimes it can have all of one, all of the other, or if it's anywhere in between, it could have both. Okay, does that kind of make sense? Okay. We're looking really at combining them just yet, but we'll get there. Okay. Roller coaster with 1,000 kilogram mass moves from point A, which is here, up to point B. What's the gravitational potential energy at B relative to point A? Okay, so when it says relative to point A, that means we're kind of looking at A as our ground level, right? Relative to ground A. So if we're starting at A and moving up 10 meters to B, we want to find out what's the potential energy at this point. Okay? So as it climbs from A to B, do you think it's gaining potential energy or losing potential energy? It's gaining because it's getting taller, right? From A to B, it's going to get higher off the ground, which means it's gaining potential energy. Okay, so from at point B, we have a mass. Okay, our potential energy is equal to mass times 9.8 times the height. So what's the height difference between A and B? 10, right? So that's where our height comes in. Okay, and potential energy is measured in joules, just like kinetic energy. So all energy and work is joules. All power is watts. Okay, any questions here? As we move from point B to point C, do we think we're gaining or losing potential energy? We're losing potential energy, right? We're decreasing our height, which means we have less potential to do work on an object at the bottom. Then as we get to point D, right, that's the lowest point on our track, right, assuming we're kind of resetting our ground level. At D, do we have any potential energy? No. No potential, right? Once we reach our lowest point, we're out of potential energy. So potential energy at B was 98,000 joules. Try one. A 70-kilogram jogger runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. What's the jogger's output of power? Okay, so as he's running up the stairs, right, he's gaining potential energy. And so we can equate the power equation to work over time. And we know that work is equal to a change in potential energy. Okay? So if you want to put this equation down, you can. But mgh over T will help us solve for power when we're overcoming gravity or we're gaining potential energy as we climb something. Because this is going to be kind of what our lab looks like today. But we're going to have to use this equation to do it. So we have a mass of 70 times 9.8 times our height. Okay, we don't really care about the individual height of each stair, right? We just care about the total height that they traveled as they went from the bottom to the top. So we had a height difference of 4.5 meters. We went upward, which means he gained potential energy, so our height needs to be positive. And then he did it in a total of 4 seconds. Does this equation part make sense? Why we're using that equation? Power is always work over time, and work is any sort of change in energy. So in this case, we went from no potential energy to all potential energy, right? As it went from the bottom of the stairs to the top of the stairs. So our change in potential energy is going to be him overcoming that gravity, right, and getting to the top. So I got about 771.75. Is that what you had it come out as? Okay. This is what our lab will look like today as well. Any questions? Okay. Yep. From this. So we just wanted the energy itself, not the power. So if we want just the energy, right, the energy that was transformed or the energy required, that means we're just looking at the work that was done, right? We don't need the power part of it. So if we know that our power was equal to 771.75, and we know it took 4 seconds to complete it, right, we can just solve for the energy transformed or the work that it took to do this, right? So we're just really solving for that mgh, right? We overcame gravity, we gained potential energy, so we're really just looking at what the potential energy part of that question was. And our unit for energy would be joules, not watts. Okay, so it's just taking a little bit of a step backward there. The cliff is a 122-meter vertical climb. The record's 4 minutes, 25 seconds. Was achieved by a 65-kilogram man. What was his average power output during the climb? Go ahead and try this one on your own.
It's a classic. There's a lot of snakes in this room, though.
Cars, and so power of cars and what they do, and when they come to a start, right, they start up, they're doing work to overcome friction or overcome a slope or whatever they have to do to get moving, right? That's what they're doing work to overcome. Okay, and each car is limited in its ability to do work by its individual horsepower rating, right? The engine, and for each car, can only convert energy so fast. Okay, so each individual car has its own kind of power rating. Okay, so our equation that we use for cars is still the same base equation, work over time, but we know that work can be a change in kinetic energy, which is where this comes from. Right, 1/2 mv squared. So you need to make sure we're thinking here, this really could be velocity final minus 1/2 m velocity initial. Right, it still could be a change in kinetic energy in which you would use final minus initial. But if there's just one velocity given, right, we would just use 1/2 mv squared. Does that kind of make sense or not so much? Okay, still is change in kinetic energy. So if you've got two velocities, right, if it wants to know the power it takes to go from 10 meters per second to 40 meters per second, we still have to do final kinetic energy minus initial to give us the work. Okay, so this equation I would suggest goes on your equation sheet as well, right? Power equals 1/2 mv squared over t, but you have to understand that that's 1 point of kinetic energy. If you've got two different velocities, you've got to do final minus initial. Okay, so if you want to write the expanded version on your equation sheet, feel free to do that as well. Okay, so we have m equal to 1,000. Our initial velocity here is 0. Final velocity is 15. And time is 4. So if I start looking at power and I say 1/2 m v squared, right, that's our final kinetic energy. Our initial kinetic energy, our system was at rest. So do we have any initial kinetic energy? No, right? So you can put the minus 0 or you can drop it. It doesn't make a difference over 4 seconds. Okay, and for most times that we're working with an engine, we want to convert that to horsepower. Okay, to give us a little bit more manageable of a number. So what would we do to convert from watts to horsepower? Yeah, divide by 746, that's right.
Is that what you do when it asks for
If-
the power of the car?
Yeah, usually when we're dealing with engines, we're going to convert them to horsepower. I'll be really specific if I want horsepower or watts. 37.7, very powerful car, or very powerful acceleration. Not so much. Right. There's 3 different terms that we need to know in terms of a spring. So what does a static something mean? What's it mean if something is static? It's not moving, right? So static means that the spring is just completely at rest. When it's compressed, what's that mean? Right, it's compressed, yes. It's been pushed together. Okay, so if I let go of the spring after it's been compressed, what does it want to do?
Go back to that static.
Right, it wants to bounce back to its static position. The same thing when I stretch the spring, if I let it go, what's it want to do? Right, it wants to reach back to its static position. So you need to know the terms static and stretched and compressed for springs. Okay? Okay, the potential energy of a spring is a little different equation. Okay, and so it looks like this. Potential energy equals 1/2 kx squared. And so k is a new variable for us. K is called a spring constant. Okay, so whenever we see a K in our equation, we have to know that we're dealing with springs because it's called the spring constant, right? So the spring constant, we're going to talk about here in just a second, but X is our displacement. And so what that means is it's measured in meters. And it's basically the distance from the spring's equilibrium that it's been stretched or compressed. Okay? So if I have a spring that's static here, and then I stretch it to be, right, this length now, here is our x distance, right? The distance that it's been stretched or compressed from its static state is the x value.
So would it be like negative when it's compressed?
Yeah, you can make it negative, but since you're going to square it, it doesn't really make a difference. So good question. Okay, the important thing to remember about the springs is that your x distance is rarely going to be given in meters because rarely do you have a spring big enough to displace it meters worth, right? It's usually going to be centimeters or millimeters that you're going to have to convert. Okay, so just something to pay attention to on your springs. Okay, K we said is the spring constant, although it's a little misleading because it's not really a constant. Each individual spring has its own spring constant. And what the spring constant tells us is basically how tough the spring is, right? How likely or how easy it is to stretch or compress. So the stronger the coil, the higher the spring constant, right? Slinky's got really low spring constant, right? But, things in vehicles maybe have a lot bigger spring constant or whatever, okay? But it just depends on how difficult it is to stretch or compress is you're going to be your spring constant. So you won't ever have to memorize spring constants, right, because they're individualized, but you could solve for them, or they could be given to you in your equation. Okay? All right, that's where we're going to stop for today.